Today we're going to talk about uniform circular motion. Now, this word uniform, what that means is that this object is moving in a circle at a constant speed. Now, the reason that I say constant speed, and I have speed in italics here, is because the velocity itself is not constant. The reason for this is because, remember, velocity is a vector, and a vector has both a magnitude and a direction. So what this means is that because the velocity vector is constantly changing direction, it's not a constant velocity. Now, how does velocity change? Well, remember, the definition of acceleration is a change in velocity. So in this case, the acceleration is changing the direction of velocity, but not the actual magnitude of velocity, because this object is moving in a circle at a constant speed. So the velocity vector is constantly changing direction from an acceleration. We call this acceleration the centripetal acceleration. Now, what centripetal means is it means center seeking. The equation that we get to find the actual magnitude of the acceleration is velocity squared, and we can just use speed here. So really it's just magnitude of velocity squared over radius, which is what your r is down there. Now I'm going to talk about the actual direction of acceleration in a bit. So don't worry about that right this second. This is how we find the magnitude of centripetal acceleration. Now, we know the centripetal force, if we use Newton's second law, which is just force equals mass times acceleration, what we're going to do is just plug in centripetal acceleration into that equation, and we get centripetal force is equal to mass times velocity squared over radius. Now, for this centripetal force, there's a lot of different forces that can cause circular motion and therefore be a centripetal force. I'll talk about that in a little bit, and we'll do a bunch of examples today so that you can that can be really clear. Now, to find the magnitude of the velocity, we're going to actually go back to like the very beginning of this class, and this just the definition of a constant velocity was distance over time. Now here, this object is moving in a circle, so the distance is actually going to be the circumference of the circle, and then the time that it takes for that object to travel one circumference will be the time for one revolution. There's actually a special name for that, which is the period, and it's denoted by a capital T. So circumference of a circle is 2 pi r over capital T, which is our period. Capital T is a period of time for one revolution, and the units of T or period are seconds per revolution. So if it takes this object 15 seconds to go around the circle one time, our period there would be 15 seconds. So it's just the number of seconds per revolution there. Now let's talk about the direction of these things. Now, usually we do a lab in class, but of course we're not in class right now, so I did it for you. Rowdy helped. You can see his little paw holding down the plate for me. So let's watch this video here, and then I'm going to talk about the direction of force, acceleration, and velocity in circular motion. Oh, no, play. Here we go. So we can see this golf ball is going around the circle. Now, if I drew the golf ball here on this little figure down here, it's at the top right-hand corner, and we can see that the sides of those plates are going to be what the force is that's keeping that golf ball in circular motion. If the plate didn't have that lip right there, that golf ball wouldn't go around in circular motion. So when the golf ball is right here at the top right-hand corner, we can see that the side of the plate is right there. That's causing this golf ball to go around in a circle right there. So if we're talking about the force that's actually causing this circular motion, would this be like the force of tension, the force of friction? It's the force of the side of the plate, right? So what do we call that? We call this the normal force, all right? So the normal force is actually the centripetal force that's causing this circular motion. Now we know that normal force is always perpendicular to whatever surface we're talking about. In this case, it's the surface of the side of that plate or the lip of the plate. So that normal force is going to be perpendicular to that surface. And as the ball moves around, that normal force is going to be changing direction. But we can see that the centripetal force, which is the normal force in this case, is always going to be directed toward the center of the circle. We can also see that, well, we also know that the acceleration, in this case centripetal acceleration, is in the direction of the net force. So that means centripetal acceleration is also directed toward the center of the circle. So that's the first important thing that I want you guys to write down and remember, is that the centripetal force and therefore the centripetal acceleration are both pointed toward the center of the circle there. Now, let's talk about velocity. So here you can see that I have cut a little one-fourth of that plate is cut out right there, and I'm going to push this golf ball. Now, what I want you to think about is what happens when it gets here. Does it go straight? Does it still follow the curve of the plate? Does it curve to the right? Or do you think it would just go straight off to a 90-degree angle to the right? What do you think? Make a prediction now. All right.
I'm not sure I understand.
Siri, shush. Now, if I play this, we're going to see what happens. All right, so let's play it. We can see that it pretty much goes straight. I know that it kind of curves in between these right here, but it's just because the lip of the plate kind of makes a weird thing. So the answer here is B. All right. Now, the reason this is the answer is because that golf ball has inertia. We know from Newton's first law that an object in motion stays in motion unless acted upon by an unbalanced force. The unbalanced force here is the lip of the plate that is causing that ball to go into circular motion. As soon as the lip of the plate is gone, it's just going to keep going in the same direction that it was going before. It doesn't have that centripetal force anymore to make it go in circular motion. So we call this tangential velocity. The velocity vector is pointed tangent to the path, which is perpendicular to both the centripetal force and the centripetal acceleration. All right. Sorry for that rude interruption by my computer and by Siri. I hope it won't happen again. I'm trying to get through this so I can post it for you guys. All right, let's talk about centripetal force. Now, I talked about how this is a general force because there are a lot of different forces that can act to cause circular motion. Some examples of this would be that golf ball going around the plate that we were just talking about. That's just the normal force from the sides of the plate that's causing the circular motion. We also can have something on a string that's being swung in a circle. That would be tension, and we'll give an example of that in a second. Also, if we have this figure down here, we can see that there's a car going around in circular motion. The force that's actually causing that motion would be friction, because if you picture this car on ice or something like that, it would just slide right off the road. So friction has to be present in order to keep that car going in a circle. Another example, in this figure right here, we have the moon going around the earth. That would be the force of gravity making that moon orbit the earth. And then something like a Ferris wheel, we can actually have a combination of forces acting to cause circular motion. In this case, it would be like the force of gravity and the normal force. And I have another example of that in a bit. So let's do an example. We have a string of 80 centimeters long, breaks when its tension is 150 newtons. What is the greatest speed at which it can be used to whirl a 1.2 kilogram stone in a horizontal circle? So first, let's write down our givens. We have that the string is 80 centimeters long. Now, can we use centimeters in physics? I hope you said no. Remember, we have to convert that to meters. Also, when they're giving us the length of the string, they're really just giving us the radius. We can see that if this string right here is our radius of the circle, because she's holding it in the center right there. So they're giving us radius. So givens, we have the length, which is the radius, is 80 centimeters, which is equal to 0.8 meters. And it says that it breaks when its tension is 150 newtons. Basically, because we're looking for the greatest speed, we want to just set tension equal to 150 newtons, because anything past that string is going to break. So we're looking for the maximum. So we get force of tension is 150 newtons. The mass of the stone is 1.2 kilograms, and we are looking for the maximum velocity that we can whirl that stone around. So Next thing I want to do is I want to write down Newton's second law. I know net force is equal to mass times acceleration. And then also, what is the force that's causing that centripetal motion? What am I going to plug in for force right there? Well, if I draw a little free body diagram on that stone, I can see that I have my force of tension right here going toward the center of the circle. Okay, so that right here, my centripetal force is going to be my force of tension. So I am going to insert that into my equation, and also I'm going to add centripetal acceleration into the equation, which is velocity squared over r. So I get force of tension is equal to mass times velocity squared over r. Now we can just plug in our numbers. I know force of tension is 150 newtons, mass is 1.2 kilograms, and radius is 0.8 meters. So now I'm going to multiply both sides by 0.8 to get rid of that 0.8 on the denominator on the right-hand side. I get 120 equals 1.2 kilograms times velocity squared. Now I'm going to divide both sides by 1.2 in order to get v squared by itself. We get 100 is equal to v squared, and then just take the square root of both sides, and we get velocity is 10 meters per second. So anything past that or at 10, that string is going to break. All right, let's do another example. We have a 4,000 kilogram car is rounding a curve of radius of 50 meters on a level road. The coefficient of friction between the tires and the road is 0.7. What is the highest speed at which the car can round the curve without sliding into the guardrail? So this goes back to the actual friction equation also. Remember that coefficient of friction, that little mu? You guys remember that? I know it was a long time ago. All right, so we're going to use this in the actual equation. So let's write down our givens. We have the mass of the car is 4,000 kilograms. The radius of the curvature is 50 meters. Our coefficient of friction, or mu, is equal to 0.7. So remember that was like the little fancy m. And then we want to know the highest speed, so we want to know velocity. Now for this, I want to draw a free body diagram just to kind of show you guys what's happening. So I have my car. I made it red because that was the color of my first car. For force of gravity down, normal force up. And then let's look at this black truck right here. I'm going to say that it is rounding the curve. We're kind of looking at this car from the back. So if it's rounding the curve to the left, then that means the force of friction is going to be pointed towards the center of that circle. So that is the direction of the force of friction. So again, this free body diagram is kind of from the back of the car. It's going into the page, okay? Now, I'm going to write down my Newton's second law. I get net force is equal to mass times centripetal acceleration. In this case, the centripetal force that's causing that circular motion is the force of friction. So I'm going to plug that in for centripetal force. So I get force of friction equals mass times centripetal acceleration, which is v squared over r. Now, I know what mass is, I know what radius is, I'm trying to solve for velocity, but I don't know what force of friction is yet. But I can find it from the other information given, because if you remember, force of friction is equal to mu times normal force. This was a long time ago, but it should be in your notes. You can also look it up online too. Force of friction is mu times normal force. Now, in this free body diagram, we can see that normal force is equal to force of gravity because we're not accelerating up or down, which means that we have balanced forces, which means normal force and force of gravity are equal. So normal force will be equal to the force of gravity, which we know is mass times acceleration of gravity. So because of that, we can just plug that in for our normal force in our force of friction equation. So we get force of friction is equal to mu times mass times acceleration of gravity. So what I'm going to do now is just plug that in for my normal force there. So we end up getting mu times mass times acceleration of gravity equals mass times velocity squared divided by radius. We can see that since we have a mass on both sides, that actually cancels out. And this is a really important thing here, because if mass didn't cancel out in this equation, that would mean that the velocity, the maximum velocity these cars could go, would be dependent on the mass. And this doesn't make sense because there's only one speed limit posted on like a freeway off-ramp, right? So if the mass mattered, they would have to post a bunch of different speed limits, which would just be ridiculous. So this is why they only post one speed limit. So now that we canceled mass out, we now get mu, which is 0.7 times the acceleration of gravity, which is 9.8 meters per second squared, equals velocity squared divided by radius, which was 50 meters. I'm going to multiply 0.7 times 9.8 and then also multiply both sides by that 50 meters to get rid of that on the denominator on the right-hand side. We end up getting 343 equals velocity squared, and then we get velocity is equal to 18.52 meters per second. So that's our answer there. Now, this is an actual calculation that an engineer would go through in order to know what kind of speed limit to post on a freeway off-ramp or a roundabout or something like that. And again, it's very important. Mass doesn't matter, right? It cancels out in the equation. Okay, so the last two examples that we've been doing are examples of horizontal circular motion. Here, we also have this thing when a circle is in the vertical direction. So something like a roller coaster or a Ferris wheel or something like that. Now, it's this type of motion is actually very exciting because this is why you feel light when you go over a bump in the road really fast, or why you feel heavy at the bottom of that curve on Goliath at Six Flags, when you almost black out. It kind of changes the way you feel because of that centripetal motion and centripetal acceleration. So we're going to talk about that today. So I do have some steps that I want to kind of go through. There's basically only one step that's kind of different for vertical circular motion. So first and foremost, you would have to write down your givens, right? And then I would want you to draw a picture and a free body diagram. The second thing, which is the different thing, is we want to label the direction of centripetal acceleration. This is really important because that will tell you which force is positive and which force is negative. And I'm going to do some examples to show you guys what I mean by that. Then we're going to use Newton's second law. Net force is equal to mass times acceleration, plug in our centripetal acceleration equation, and then solve for the unknown variable. So every other step in this is pretty much the same, but it's that step number 2 that's really important here. Because remember, it's net force equals mass times acceleration. It's not just one force, it's just the net force. Also, if the problem is asking you for the apparent weight of something, really it's just asking you for the normal force, all right? Normal force is not always equal to force of gravity, and the reason you feel lighter or heavier in an elevator or on a roller coaster or something like that is because of the normal force. The normal force is always the force that you feel, okay? All right, let's do an example. We have example number 3, a 500 kilogram car. It's a very light car. It's like a little smart car or something like that. Is speeding toward a hill which has a radius of 240 meters. What is the fastest speed the car can go in meters per second without coming off the road? So givens here, we have the mass of the car is 500 kilograms. The radius of curvature of the road is 240 meters. We're looking for velocity. What's the fastest speed the car can go? And then it says without coming off the road. So when a car comes off the road is no longer in contact with the car. So therefore, there's no more normal force. So what's happening here is the normal force is approaching 0. So what we can do here is it's kind of like the tension that's breaking, remember, that we did for the first example. You can just set normal force equal to 0, and then that will give you the fastest speed. So second step here is we want to draw our free body diagram. I know that in the free body diagram, force of gravity is down, normal force is up. Now, the other important step here is to find the direction of centripetal acceleration. So if we look at this picture right here, we can see that the curve goes downward like this, which means that the center of the circle is down here. So remember, centripetal acceleration points toward the center of the circle, which means that centripetal acceleration is down. What that tells us here is that in our Newton's second law equation, force of gravity will be positive, normal force will be negative. So for net force is equal to mass times acceleration, net force will be made up of force of gravity minus normal force, and that will be equal to mass times centripetal acceleration, which is v squared over r. Now, I also know that the normal force is approaching 0, so I'm just going to plug in 0 for that normal force. I also know that force of gravity is equal to mass times acceleration of gravity. So I get mass times acceleration of gravity equals mass times velocity squared divided by radius. And look at that. Mass, again, is on both sides of the equation in every term. So I can actually cancel that out right there. So mass cancels out. I then get acceleration of gravity, which is 9.8 meters per second squared, is equal to v squared divided by the radius, which is 240 meters. So now I'm going to multiply both sides by 240 to get rid of that on the denominator on the right-hand side, and I get 2,353 equals velocity squared. I will take the square root of both sides, and I get velocity is equal to 48.5 meters per second. So that's our answer there. Now, this radius of curvature of the road is pretty big, so you have to go pretty fast in order to, come off the road and get some air. Don't tell your parents I told you this, but if the radius of curvature is smaller, we know that this radius is on the denominator, right? So if it's smaller, then you actually don't need as much speed in order to make that normal force be zero. So don't do that. But because the radius is so big, that's why you would need to go so fast. The rule of thumb here is to go from meters per second to miles per hour, I think is like 2.2 miles per hour in meters per second ish. So you have to go about 100 miles per hour in order to make that normal force go to zero. So if the radius is smaller, it wouldn't be as fast in order for you to make that normal force go to zero. But don't do that. Don't try this at home, please. Example number 4. We have a Ferris wheel, 26 meters in diameter, rotates 4 times per minute. What is the 56 kilogram passenger's apparent weight at the bottom? So our givens, we have the radius. It says diameter is 26 meters. So is that the radius? No, we have to divide that number by 2. So we end up getting the radius is 13 meters. We have that it rotates 4 times per minute. So this is giving you that period. Okay, remember we talked about period at the very beginning of this lecture. So remember, the period of time for one revolution, that's what that capital T is. So we want this in seconds. So on the top of that fraction, when we're talking about period, that's going to be 60 seconds because it's per minute. And then I know that it's rotating 4 times. So how we find period here is I have 60 seconds for 4 rotations, and then what I'm going to do to find how much time for one rotation is we just divide 60 by 4. So 60 divided by 4 is 15 seconds per one rotation, and that's what a period is equal to, okay? Now, from this, we actually need to find the velocity, but let's finish writing down our givens and then we'll find velocity. So we also know that the mass of the person is 56 kilograms, and then we want to know the apparent weight at the bottom, which remember, we're looking for normal force when we're looking for apparent weight. Now, first and foremost, let's find the velocity. We know that velocity or speed is equal to 2 pi r over period because we're talking about circular motion here. It's circumference over the time for one revolution. So if we plug in our numbers here, we get 2 times pi times 13 meters divided by 15 seconds, and we end up getting 5.45 meters per second for our velocity. So now we can actually solve for what we're looking for. Now let's draw a free body diagram. It looks a lot like the one that we just drew. We have force of gravity down and normal force up, but now we're talking about when we're at the very bottom of this Ferris wheel right here. So if we're at the bottom, notice how centripetal acceleration is now up because again, centripetal acceleration is pointed toward the center of the circle. So our centripetal acceleration is upward. So now we're going to write down Newton's second law. We get net force is equal to mass times centripetal acceleration. Now, the positive force here is going to be normal force because that's the direction of centripetal acceleration. So we'll get normal force minus the force of gravity because the force of gravity is pointed in the negative direction. So we get normal force minus the force of gravity equals mass times velocity squared divided by radius. Now I know force of gravity is equal to mass times acceleration of gravity, so I'm just going to plug that in there, and then we're solving for normal force. So I'm going to add mass times acceleration of gravity to both sides to get that normal force by itself. And now we know everything, and now we can plug in our numbers and solve. So we get normal force is equal to the mass 56 kilograms times velocity squared 5.45 squared divided by the radius 13 meters plus mass 56 kilograms times acceleration of gravity 9.8 meters per second squared. Plug this all into my calculator and I end up getting 676.75 newtons. So there's our answer there. This will actually be heavier than what she normally feels. And you can kind of see that from this equation right here. This is what she normally feels when there's no centripetal acceleration, because if there was no acceleration, normal force would be equal to the force of gravity. But since we have that centripetal acceleration, we have an additional weighty feeling. So this adds to that. She feels heavier at the very bottom of the Ferris wheel. All right, last example. We have Sheila, whose mass is 62 kilograms, is riding a roller coaster. The turning radius of the top of the loop is 12 meters. Sheila is upside down at the top of the loop and experiencing a normal force, which is 1/2 of her weight. Draw a free body diagram and determine Sheila's speed. So we first and foremost write down our givens. We get that Sheila's mass is 62 kilograms. The radius of curvature is 12 meters. And then it also says that the normal force, so she's experiencing a normal force, which is 1/2 of her weight. Now remember, weight is just the force of gravity. So I'm going to say normal force is equal to 0.5 times the force of gravity. All right, it's just 1/2 of her weight. And we want to know what the speed is at the very top. So let's draw that free body diagram that they're talking about. And I'm actually going to draw it into this loop right here. Here's our roller coaster at the very top of the loop. Now we know that the force of gravity is down, and because we're upside down at the top there, the normal force is actually down as well, which, yes, I know, that's kind of mind-blowing. But because we're upside down there, the normal force is the force of the track on the roller coaster. That's also directed downward. I know that this is really weird and it kind of seems like this roller coaster should just be falling down, but remember, this direction, the direction of the net force, gives the direction of the acceleration. It doesn't give direction of velocity. Velocity, this roller coaster is going to the left at the top there, right? That's the direction of that tangential velocity. And what this acceleration is doing is just changing the direction of that tangential velocity. So no, this roller coaster is not going to fall down. It's going to keep going and go around this curvature here, okay? So now what we want to do is we want to write down our Newton's second law equation. We get net force is equal to mass times centripetal acceleration. The net force in this case is going to be both the force of gravity and the normal force, and those are both pointed in the positive direction because that positive direction is the direction of the centripetal acceleration. So we get normal force plus the force of gravity equals mass times velocity squared divided by radius. Now, normal force in this case we know is equal to 1/2 of her weight. So I'm just going to plug in 0.5 times force of gravity in for normal force. And so we end up getting 0.5 Fg plus 1 Fg. So that just becomes 1.5 times mass times acceleration of gravity, because that's what Fg is. Our weight is just mass times acceleration of gravity. And here, mass actually cancels out. So her mass actually doesn't really matter. So we get that. Mass cancels out. And we end up getting 1.5 times acceleration of gravity, which is 9.8 meters per second squared, equals velocity squared divided by the radius, which was 12 meters. I'm going to multiply 1.5 times 9.8 and also multiply that by 12 meters to get rid of that on the denominator on the right-hand side. We end up getting velocity squared is equal to 176.4, and then we will take the square root of both sides to get a velocity of 13.3 meters per second. constant. Now, notice how in a lot of these equations, mass canceled out. That won't happen every single time, all right? So it only happens when we have a mass in every single term, okay? So if I had a normal force that wasn't equal to something like the force of gravity, half of the force of gravity, then this mass wouldn't have canceled out. So be really careful there. Mass doesn't always cancel out. All right, so we did a bunch of examples today. I'm sorry this took so long, but I wanted to make sure that I kind of gave you every single type of different example that you could get with these problems. It's a lot of information. We basically did a whole week's worth of work in one lecture. Okay, so you guys are working really hard. I'm very, very proud of you. Please email me if you have any questions this week. Come to office hours on Friday, and I will hopefully see you later. All right, bye guys. Have a good week.